different audience. And so I will go back to photo emission and continue talking about magnetic phases and phase transitions, but now on the example of a very simple system of gadolinium metal. So gadolinium is a rare earth. It's situated directly in the middle of the lanthanides. Hi. There? Okay. No? Okay. So it's directly in the middle of the lanthanides, so it's got a half-filled 4F shell, and this creates a large magnetic moment, but zero orbital momentum. And yeah, these 4F electrons are strongly bound deeply below the Fermi level, and they have no spatial overlap between neighboring atoms, so there is no direct exchange interaction between them, but there is an overlap with the 5d6 valence electrons, here situated around the Fermi level, and there's an exchange interaction which spin polarizes these valence electrons. And because there is no overlap between them, there is an exchange interaction as well, which aligns neighboring atomic moments ferromagnetically. So this is the RB-Y interaction, which is typical for the heavy lanthanides. And now what we are doing is we prepare a 100 angstrom thick gadolinium film on a tungsten substrate, and we do tons of photo emission, so we pump it really hard with a laser pulse, which induces a phase transition. And the laser pulse, so the energy is 4 millijoule per square centimeter for fluence, and the photon energy is 1.6 electron volts, so it's a 300 kilohertz titanium sapphire laser. And to probe the band structure afterwards, we use the power harmonics of the titanium sapphire, which has then 6.3 electron volts. So this is not very much, so we can see the region near the Fermi level. So here is the step calculation towards it up, and what we can photo emit is the state marked here by this process, which is a majority spin surface state of gadolinium. It's also a 5D state, and it is majority spin, so there is a corresponding exchange to the minority spin partner, which is situated above the Fermi level, so it's unoccupied and we don't see it in photo emission. So now a spin result spectrum looks like this. So we find more majority spin electrons, which are shown in blue, and the ratio between majority and minority spin electrons is the spin polarization. Now, when we heat the sample, simply thermally with a filament, then we see that the spin polarization is decreasing and going to zero at the Curie temperature. This is happening in the majority surface state, so there are more minority spin electrons coming into the state, and the process is called spin mixing. And when we have a look at the binding energy here of the peak, we see the peak is also shifting towards the Fermi energy. And what can be seen in scanning tunneling spectroscopy is that the minority spin partner is also shifting down to the Fermi level, so the peaks shift towards each other, the exchange splitting decreases. And this is the classical stoner-like process, which is known since the 1930s. So now we want to, so we have stoner-like exchange splitting decreasing and spin mixing process both in this state, but the exchange splitting, as you can see, remains. So it's still 400 millielectron volts at the Curie temperature, although the phase is already paramagnetic. So this is a very strange behavior for a magnet. And to get a deeper insight into this, we started to look at this with photo emission and induced this phase transition not by thermal heating, by thermal excitation, but by a laser excitation of the electrons. And so now here in the middle you see energy and time delay spectrum. The photo emitted intensity is the color, And this is spin integrated. And on the left side, you see a corresponding spin integrated spectrum at the time delay of this black arrow. So before the pump pulse, nothing has happened yet. And on the right side, you see the corresponding spin resolved spectrum. So I have to add that spin resolution is hard to do. So the count rates are a factor of 100 lower. That's why there are not many spin resolved spectra that we can take. So we have to decide where to make spin resolved cuts. And we can do the experiment very easily with spin integrated. Okay, so now when we excite the sample here at 0 pump probe delay, we see a lot of things happening. So first, here at 0.2 picoseconds, we find that electrons are excited from the surface state above the Fermi energy. So here a lot of intensity is created. The intensity is going down below the Fermi level, which is here. And in the spin resolved spectrum, of course, we find the same processes, but the spin polarization, so the ratio between blue and red, between majority and minority spin electrons remains. And going to larger time delays, for example 5 picoseconds, we find the state is repopulated again, and now it started to shift towards the Fermi level, just like in the thermal heating, in the phase transition. So this might be a decrease of the exchange splitting, but in the spin resolved spectrum, we still don't see a change of the spin polarization, neither at 10 nor at 15 picoseconds. And going to large time delay, so here 240 picoseconds, so from here on, from 2 picoseconds we find everything is relaxed again, so the gray curve here is exactly on top of the black one. So, to summarize this laser heated experiment, we find 3 processes. First, the very fast heating of the electrons, which is below our time resolution. The time of our laser pulses are, so cross correlation between the pulses is 70 femtoseconds. Then we find a shift in the binding energy, which probably is an exchange splitting decreasing on a time scale of 0.6 picoseconds, and we don't see much happening in spin. So let's have a closer look at the spin. Besides these vertical cuts at a constant time delay, we can also make horizontal cuts at constant energies. So this is what we did here, for example, for minus 200 and minus 120 millielectron volts, which is the initial binding energy of the surface state and the energy of the maximum peak shift. And we see a lot of things happening in the photo-emitted intensity because the peak is depopulated and then it shifts. But the ratio between majority and minority spin always roughly remains. So when we gather all this information in one plot, then we find that if anything is happening at all in the spin, then it's decreasing at very large times, so larger than 10 picoseconds. And now when we fit an exponential into these data points, then we find the decay at 15 plus minus 8 picoseconds. So in this experiment, we find 3 processes again. So when we fit the Fermi function, we can extract the temperature of the electrons. And we see here that it's going up really very fast. This is on the time scale lower than 70 femtoseconds. And demagnetization has been observed on this time scale. And this was in the magnetic second harmonic generation, so which is very surface sensitive. So we believe that the surface is already demagnetized by this heating of the electrons because the surface state is depopulated and it's got a large magnetic moment contributing to the surface magnetism of gravity. Then we can model the decay of the electron in temperature by assuming that the electrons transfer their energy to the lattice, so electron performance scattering. And this is exactly the temporal behavior that we find in the binding energy shift here. And this is what's happening on the time scale of 0.6 picoseconds. And also a demagnetization has been observed on this time scale in the magnetic signals of X-ray magnetic circular dichroism and the magneto-optical Kerr effect. And then much later, the spin polarization of the surface state changes, and Also, a demagnetization has been found on this time scale in photo emission from the 4F electrons deeply below the Fermi level, which show a magnetic linear dichroism, and this is decreasing on a time scale of 14-15 milliseconds. So it seems as if the spins still stay aligned. And to compare this to the beginning, to the thermal equilibrium phase transition, we take these two plots and put them into one, with the spin polarization on the vertical and the peak position on the horizontal axis. And now we see that while the peak shifts forward, there's not much change in spin. And when it's shifting backward, the spin is a little decreased. So this is the laser-heated non-equilibrium experiment. And now we take the data from the beginning, the thermal equilibrium, and add them here. And we see that at the same values of the peak shift, the spin polarization is already lost because the magnetic phase transition from ferro to paramagnetic is already here. So it's already at the Curie temperature when the peak is shifting this far. So in this experiment, we find in the equilibrium phase transition the Stoner-like peak shift accompanied by the spin mixing process, while in the laser-driven phase transition, we also find the Stoner-like peak shift without the spin mixing process. And this can be understood by going back to the picture of the RKKY interaction from the beginning. So what we do in this laser-heated experiment is we directly excite the 5D electrons, and they are getting energy, so they have to do something with the energy, and what they do is they start to demagnetize in a Stoner-like way, because their spins still stay aligned to the 4F electrons, because this interaction at every lattice side between the 5D and the 4F is much stronger than between the atoms. So this forbids the spin mixing process. And what you've seen in this talk is that, as I promised in the title, by laser excitation we can separate exchange splitting from spin mixing in the aluminium, and that this is due to the nature of the 4F RKKY interaction. And what I also wanted to remember is that there are three processes or three things contributing to the magnetism of the aluminium, and so this leads to three time scales in the ultra-fast laser-induced demagnetization. You can read the full story again in this paper. And with that, I want to thank a lot of people, and I want to thank you for your attention.
Thank you very much. Great talk. The talk is now open for questions. Yes.
I have a very basic question. You say the magnetization of the d electrons comes from the f electrons.
Yes.
Why do you call it the Stoner type of magnetism?
So it's a spin mixing prototype, classically.
It's more like a Kondo type, or not?
Yes. Okay, but it's always referred to in literature. This shift of the band energies is always referred to as Stoner-like process. So it's always divided into Stoner and spin mixing, and the spin mixing is just when the spin in one state is becoming less pure, and the Stoner-like is this shift. So yeah, it's the decreasing of exchange.
The occupation balance between minority and majority bands, that's what we call Stoner.
Yes. Yes. So the original Stoner magnets are pretty ferromagnets, but yeah, they also do spin mixing, so this is always a mixture of both.
Yes.
In the first slide, you explained the energy diagram of this element. Oh.
Which
the
slide?
first slide.
Fourth.
Yeah, the introduction part.
I don't know.
The energy diagram.
The energy
show the spin majority and the spin minority.
This one.
Yeah, would you please explain, this, and I'm a little confused. Yeah.
Okay, so this is the density of states, roughly sketched, where you find the, so from when you add the band structure up for all, so this is the momentum here. This is energy over momentum, so you get the band structure.
But I mean, how I related pump and prop process with this energy diagram?
What
No,
are the energy
it's
scales?
The
I
energy.
think he's asking what are the energy scales when you compare the pump and probe.
Okay. What? So you mean that with a pump we can pump, only from the surface state?
I think the energy scales are right there on the band structure, and then you see the 6.2 eV and 1.6 eV there.
So you have to subtract the work function, which is 3.7 electron volts, and then end up somewhere close to.
Right. Any more questions? All right. If there are no more questions, let's thank the speakers.